variable charts, the X and R bar charts, and those charts are specific to data that is continuous, you know, like we talked about, height, weight, length, measurements of some sort. Attribute charts, on the other hand, are charts that measure good or bad, like percent defective, or the number of problems or the number of things someone might have done correctly. We do this with two different charts. The first is a P chart, and we define that basically as a percentage of defective units. The percentage of defective units will follow something called a binomial distribution, which is unique and allows us to do certain things. The second type of chart that's an attribute chart is this thing called a C chart. So a C chart is a kind of a count of defective units or a count of correct units, and it follows a Poisson distribution, which again allows us to do particular things with it. So with that, I am going to talk in a little more depth first about P charts, and then we'll move on to talking about C charts. So as I said before, P charts, or the percent of defective units, they follow what's called a binomial distribution. So what's important about a binomial distribution is that it acts kind of normal but has these block pieces to it, which is important because it enables us to calculate the standard deviation and mean slightly differently. And as a matter of fact, one of the things we like about this type of distribution is that it's sort of black and white, or in this case green and blue. You either are defective or you are not defective. There are no other options. So either you made the free throw, as I often talk about in class, or you missed the free throw, but there is no partial free throw. So this is a useful measure and a useful thing to know, this binomial distribution, because it enables us to calculate the mean slightly differently, and again the standard deviation. It's a little easier actually, so that's of course even better. So P charts, we can create control limits for P charts, and we can do this because of the central limit theorem and because we know it has this binomial distribution. So the central limit theorem enables us to assume that there is a normal distribution for the sample statistics that we're after, and we know from the previous slide that enough observations we're going to have a collection sort of in the center, just like we have learned before with the normal distribution. So the bulk of our observations we expect to be right here in the center spot. So with that, we can then easily calculate the standard deviation of P and again compute the limits, very similar to the other methods that we have done. The only difference really is the standard deviation. So once we've calculated P bar, we can then take P bar times 1 minus P bar. Again, that goes back to the yes or no. Either you made the free throw or you missed it. There is no other option, so that's thus the P times 1 minus P bar. And then we're going to divide it by our sample size. So be mindful that it's the number of observations in each sample. So we're going to have a whole bunch of samples, and then within each observation we're going to have, 100 or 10 or something like that. We're going to multiply it times Z times our standard deviation of P, very similar to before. So let's go ahead then with this as sort of a background and try a problem. So here we have an example of a proportion problem where we're going to compute the upper and lower control limits of P bar based on this information here. So this is example 6.3. Here we have computed the average number of defects to be 2%. So that means that P bar is equal to 2%. And we have a sample size of 100, so we know now that N is equal to 100, and we want to compute the upper and lower control limits set at 3 sigma. So first thing, let's put down the information that's relevant. So we've got our p-bar, we know, is 0.02, right? Because it's 2%, so we're going to convert that to a decimal, and we know that it's going to be 0.2%. We also know that our n is going to equal 100, because it tells us that in the problem. And we also know that we want our z value to equal 3, which we know is how many percent? Remember, it's 99.7, 3% of the observations we want this to consider. And so I'm just doing that as a little review. You don't really need that in there, but just so you know. Now, we're going to go ahead then first, and we need to calculate our standard deviation of p. So you notice I've got this twice. So the reason I have it twice is so that I could use this one here to sort of fill in the numbers. So I'm going to take out p bar, and I'm going to put in 0.02, and you'll notice that the bar remains there, but that's because of the way the program works. So really you wouldn't need that there. And then 1 minus 0.02. I don't know why it didn't show it there. Let's see if I can just delete the whole thing. Here we go, 0.02. There we go. And then our n, remember, is 100. And this is important, once again, because we don't want to think it's, you know, the number of samples, say 12 or whatever. So we have it as 100. So that, we'll go ahead and run that through our calculator, and we are able to then quickly find out will equal 0.0143. So 0.0143. Whoops, where'd that go? 0.0143. That this will equal 0.0143. So now we've got our standard deviation of p. We can take this and go plug it into our formula right over here. So let's do that, and it's going to be computed exactly like we have done previous calculations to compute the upper and lower control limit. So we plug this in and we get the following. We find that the upper control limit would be roughly 6.3% errors, and then we find the lower control limit is actually negative 0.0229, but we will always round that to 0. We're never going to have negative percent defects. So now let's translate this over to words. What does this actually mean? So what this means is that when we have a sample that on average has 2% errors, we can expect errors to range between 0 and 6.3%, 99.73% of the time. So our model, said differently I guess, our model suggests that we should obtain errors between 0 and 6%. So if we were to find someone who was averaging 7, 8, 10% errors in each observation, we would know we've got a problem. So this helps us understand what is normal and what is outside of normal. Remember, we started this whole discussion about the importance of determining first what is normal. And this is an exact explanation, if you will, as to why you have to first get enough observations to determine what's normal. Because if we expected people to be perfect all the time, then you know, that's just unrealistic, because here we have this large sample and we have determined that people make errors. They make between 0 and 6% errors, and so we need to consider that in our decisions and that sort of thing. So thus the importance of collecting the data first before we, you know, start making rash decisions about people, their performance or whatever. Okay, So this was P, the percentage of defects, and we calculate P bar first by taking the sum of all the defects, dividing by the total observations, which we haven't really done. I gave you in this problem the number of defects, or the percent, the P bar essentially. So in this next problem, I'm going to use data to show you how to determine what P bar is. So here you have the same data as you have in your handout on page, oh, it's probably page 4. It's example 6.4, practice P-chart usage. The numbers are in a little bit different format. I have them sort of listed in a list down there, but at the very top of the page you can see this as well as the next slide after this. So what I want to show you here is how to compute P bar. So first of all, you have to have the sample numbers. So we've got 1 to 10 on this side and 11 to 20 here, because I couldn't really list 20 on this, in this format. On your page you'll see that it's listed in a column, but it's the same data. And here we have the number of errors. So this means that in sample number 1, which remember was 100 units, we found 6 errors. So remember that each one of these 20 samples all represents 100 units, and we are interested in the average number of defective units. So this is not 6 errors out of 6, it is 6 out of 100, or 6% defective units. So we sum up our defective units and we get this 80. Now, another thing we can do is look at this graphically. Now, you'll notice here I've got the upper and the lower control limits. You wouldn't be able to put those in, but you could certainly see where the dots fell in this type of a setup. Sometimes it's easier to see if you have outliers, so maybe even without the upper and lower control limits, you might be able to see that this one looks a little bit like an outlier, but maybe not. Of course, you'd have to compute the P bar first. So let me just show you how to compute the P bar, and then you should be on your way to doing these. Okay, so here we have added up, I have written out for you the total number of errors, which is 80, and we took that from right over here. We had added all the errors up and we end up with 80 right there. So that goes in our numerator. We have that right there. And then in the denominator, we've got the 100, which is our sample size, multiplied by 20, which is our number of observations. When we run this through our calculator, we got this 0.04, or 4% errors. We then calculate the standard deviation exactly the same as we had previously, right? So we take, you either have an error or you don't. So we have 4% errors and essentially 96% no errors. Divide that by our sample size, which is 100, same as our previous problem. And we find out that 0.02 is the number of errors, so 2% errors. So depending on the number of standard deviations we want to consider, and in this case we're considering 3 standard deviations, so we then just take 0.04, we multiply it times 3 times 2, or 2%, and we find that the upper control limit for this problem would be 10%, and the lower control limit, once again, we round it up to 0 because we don't want to have a negative number. So we find that a person should have between 0 and 10 defective units. And that's really all there is to it. So there are a couple important things to remember about P-charts. First of all, they're an attribute chart. They can be used for things that have 2 optional outcomes, yes or no, 1 or 2. I mean, there is, you make the basket, you miss the basket. You cleaned the room, you didn't clean the room. There is no grounds for interpretation here. You got the question right, you got the question wrong. So a P-chart is what this is. It represents a percentage of defects. And another important piece of information, I suppose, with all of this is that the type of distribution that the P-chart takes on is the binomial distribution, which acts normal in many ways, but has this bit about the either you have it or you don't have it, and that enables us to then calculate the standard deviation slightly differently, which is, you know, way easier really than standard deviation of a continuous sample. So you should try a few problems like this in the text, and hopefully this little video will help you at least some. I'm going to continue on now and talk about C charts, which are another attribute chart. So now I'm going to talk about C charts. C charts are the other type of attribute chart. And in a C chart, much like the P chart, it has a special distribution. This one is called a Poisson distribution, and that enables us to actually make things even easier than in the P chart. So we like the C charts because essentially it's just the average number of defects. It's not, there is no possible maximum. So in this, first of all, what you see in front of you is a nice, kind of a skewed but nice normal distribution here with all these little columns. And the columns represent the idea that it's just on average how many are wrong or right, if you will, depending on the circumstances. But the unique thing that we like about the Poisson distribution is that it enables us to, or the central limit theorem enables us to calculate the standard deviation by just taking the square root of the mean. And that is because in a Poisson distribution, the variance is equal to the mean. So if you think about that, that really makes things easy. And indeed, notice here, C bar, that's just like P bar, X bar, etc., the average number of defects. And we just take the square root of that to get the standard deviation. So imagine for a moment if we were able to just take the square root of the mean of the means back in the X bars, it would make our life so much easier. But because the data is continuous with the X bar, we can't really do that. But these I find simple enough to compute. So in the case of the C charts, a couple things to keep in mind. I think students sometimes get these confused with P charts, and it's understandable. They're both attribute charts. But the thing about C charts is there is no maximum. So in the P charts, I talked to you a little about free throws. Well, free throws, there is a maximum. You can only get as many free throws, you can only make as many free throws in a game as you are given to make. You know, like if you don't go to the free throw line, if you're never fouled, you cannot make any free throws, and you can only make as many as you go to the free throw line for. So when you look at basketball statistics, you see those always as percentages, and that's because either you made it or you didn't make it. On the other hand, steals or rebounds, those are not captured the same way. What you find when you look at steals and rebounds is you find that it's a number. It's a 4, 2, 7, 8, whatever. And that's because there isn't a maximum number of rebounds. I mean, imagine for a moment if Anthony Davis was out playing with Orono High School, he would get a rebound on every single ball because he is a foot taller than everybody at Orono High School. So it's kind of an infinite number. So the C bar allows us to capture some control limits when we kind of don't really know how many, you know, defects or steals or whatever could occur. Now, for those of you who don't know what I'm talking about with steals and rebounds in basketball, you know, I guess another example might be defects on a golf ball. This is the one they use in the textbook. They say that, you know, someone's job might be to inspect golf balls, Titleist golf balls, or any kind of golf balls for that matter, or Camelback, you know, cups for defects. So does it have a cut in the paint? Does it have a dimple? Does it have whatever? Again, it could have an infinite number. There is no limit. If the paint machine went wild while painting one of these things, there could be an infinite number. So the idea is the C bar is you just don't know how many defects there could possibly be. And we like the fact that it has this Poisson distribution because this enables us to just take the square root of the mean, because we know that the mean is equal to the variance. So we're going to go now and do a problem using the C-bar chart, and I'll show you how easy it is to do. So this problem I stole from the textbook. You'll see it is the C chart for a cab company. In 9 days there were 54 complaints, so we had on average 6 complaints per day. So C bar is, of course, 6 plus, we're interested in 3 standard deviations. We're always seems to be interested in standard deviation, 3, so we're looking at 99.73%. So we multiply 3 times the square root of C. So we'll just take 3 times the square root of 6, 3 standard deviations, times the square root of 6, and that will yield 13.35. So what does the 13.35 mean? It means that it's pretty much acceptable to get as many as 13 complaints in a day for this cab company versus expecting no complaints. And so if we get 13 in a day, hey, you know, that's within what we expect, and it goes from 0 to 13 once again, because if we were to subtract 3 times the square root of 6, we would have a negative number, so we just roll that up to 0. We're not going to have negative complaints, of course, in one day. So this is a simple example, and then let me just show you one where we have to actually compute C bar. So here we have a problem from the book, 622, and we're going to answer these questions. So first we'll read the problem. An ad agency tracks complaints by the week received about billboards in the city. All right, so week 1, 4, week 2, 5, etc. What type of control chart would we use to monitor the process? Well, of course we know it's a C chart because I just told you I was going to work another problem, but we know it's a C chart because there's an unlimited number of possible complaints, right? So there we go. Number A is fixed. It's a C chart because of the unlimited number of possible complaints. What are the 3 sigma control limits for this process? Assume the historical complaint rate is unknown. So here we're going to compute the upper and lower control limit for using a C bar calculation. So I'd like you to do this on your own, and pause this video, do it, and then I'm going to do it as well, and then you can check your answer against mine. So you can see first I calculated C bar as the sum of 4 plus 5 plus 4 plus 11 plus 3 plus 9. I divided that by 5 and I got 6 for my C bar. I just took these numbers, I added them up. I divided by 5 because I divided by 6 because I had 6 days, and this sums up to 36, and thus 6 is my C bar. So then I computed my upper and lower control limit by taking C plus 3 because I was interested in 99.73% of the observations. I multiplied that by the square root of 6, which should be about 2.45, and that gives me an upper control limit of 13.35 and a lower control limit of negative 1.35, but that rounds to 0. So that's the upper and lower control limit of complaints that we expect. Now it asks us in part C if it's in control, and we're going to say yes, it is in control, because all of the observations are inside of the control limits. Now for part D it asks us, assume now that we've got the historical rate has been 4 calls a week. What would the 3 sigma control limits be for this process? And is this in control? All right, so now they're saying, okay, instead of 6 being C bar, now C bar is 4. And so they want to know if this would be in control. So now we're changing our C bar to 4, and our standard deviation is now going to be 2, right? Because the square root of 4 is 2. So now we're going to calculate our upper and lower control limit, and we're going to come up with 10 and 0. And then they want to know, okay, so now is the process in control? So no, it's not, because on day 4 we've got 11 complaints when we're saying that we really want to have an upper control limit of 10. So we computed exactly the same as before, but our C bar is 4 now. So I'll go ahead and calculate that down here for you. And again, it would be good if you did that separate from me and then come back and check. So as you can see by my calculations here, I've just replaced the previous C bar of 6 with 4, and I've calculated the upper and lower control limits, and I find that 10 is the upper control limit and 0 is the lower control limit. So indeed, week 4 exceeds the new upper control limit. So much like I sort of summarized the P chart, this summarizes the C chart really. Basically, we use the C chart when we have an unlimited number of possible complaints, which is what I have here, unlimited number of possible events, whatever they are. We calculate C bar by taking the square root of the mean because of the type of distribution. That's what allows us to just take the square root of the mean. If we didn't have this, lovely Poisson distribution, we wouldn't be able to do this. We would have to do it a different way. So we use it for unlimited defects, and we compute it in a relatively simple way. So hopefully this helps you understand a little bit more about attribute charts, and you can use this to review from, and maybe I'll throw in a clicker question or two about one of these things here at the end. So those of you that have watched, you've not only learned a few extra things, but you should be able to answer some questions pretty quickly and easily. So have a great day. Thanks for listening. Bye.